So buffers resist changes in pH. They're a two-way street. They absorb strong acids into the buffered system, keep the pH close to where it was beforehand. They absorb strong bases into the system, keep the pH close to where it is. Okay? Remember that that's all about that equilibrium that we wrote in the last video. The equilibrium that contains concentration of a weak conjugate pair, right? So one thing you'll be asked to do a lot of the time is, hey, what about these chemical systems? Could it possibly be a buffer? If I get equal amounts of each one of these species together in the same solution, will it act to resist changes in pH? And for now, all that you guys have to look out for are weak conjugate pairs. And if you see those weak conjugate pairs, and they're going to be there and around the same concentration, then the answer to, hey, is this a buffer, is yes. If you don't see weak conjugate pairs, conjugates from weak species, that's all you need. An acid and a base, but they're conjugates, right? If you don't see that, right, then you're not left with a buffered system. And it can't be assured to resist changes in pH. So let's just take a look at a couple different scenarios to make sure that we drive that point home. Because even understanding that you could possibly have a buffer is the first step in approaching a buffer calculation. So what about HCl and NaOH? All of those identification steps we did the previous weeks, they apply here as well. I take a look at HCl, right? I'm going to have an equal amount of NaOH there, or around an equal amount. HCl is a strong acid. NaOH is a strong base. We do our same recognition steps here. Can I have a buffer with strong species there? And the answer is no, absolutely not. There's no way this could be a buffer, right? And in fact, you know what happens. We wrote this down already. Cl- is a spectator ion. It's the conjugate of a strong species. Na+, spectator ion, conjugate of a strong species. If these two things were reacted in equal amounts, you would H+ plus OH- going in one direction to form H2O. What do you need for a buffer? Weak conjugates and an equilibrium. And do you see any of that there? Well, no. If I add more acid, it's just going to add more acid. If I add more base, it's just going to add more base. This reaction only goes in one direction. It doesn't resist changes in pH. Okay, so let's go on to the next case here. What about HF and NH3? Could this possibly be a buffer? Well, this is a weak species. This is a weak acid, HF. It's not one of my strong acids I've memorized. NH3, yep, that's a weak base. We've been over that as a weak base before. This has a separate Ka, this has a separate Kb. Yeah, we're ready to go here. All right, except this is a weak acid and a weak base being mixed, but are they conjugates? And the answer is no. They are not conjugates. And actually, the chemistry is really complicated here, and we haven't gone over a mixture of a weak species with another weak species. But the big important thing to know here is, all you look for are the presence of weak conjugate pairs. The conjugate of HF is F-. Is F- the base in solution? No. The conjugate of NH3 is NH4+. Is NH4+ in solution? No. You need weak conjugate pairs to make an acid. Down here then, what about a solution I make with equal amounts of HF and KF, right? HF I know is a weak acid. KF I know is a salt, and it breaks into a K+ and an F-. And I know that K+ is the conjugate of a strong species, so as a spectator ion, it doesn't really matter. Oh, so a solution with HF and KF would really have HF and F- in it. So is this a solution that could act like a buffer? And the answer is absolutely yes. So where do you expect, right, the pH for this buffer to be around? Remember, if we identify a weak conjugate acid-base pair in solution, the pH is going to be close to the pKa. Now for HF and KF, I go to the acid and I look up its Ka. And the Ka for HF in a table that I looked up, and maybe it's the same as the table that you have in the back of your book on your appendices, is 6.6 times 10 to the minus 4. So will this form a buffer? Absolutely it will. This buffer will have a pH that's near the negative log of 6.6 times 10 to the minus 4. So it's going to have a pH that's near 3.18. Okay. So if I want to construct a solution with a pH that's near that, and I want it to resist changes in pH, I want to make a buffer, all right? This would be an appropriate choice to hit that pH, right? Or be close to it. Generally, just as like a rule of thumb, we say that a buffer has a plus or minus 1 sort of capacity, a plus or minus 1 range of where it could be effective. So this buffer, theoretically, just as a quick little rule of thumb, could be good from about pH 4 to about pH 2, right? Ideally, if I want a pH that's near 3, this would be a great choice, okay? No way, can't be a buffer. Nope, not a buffer, don't have a conjugate acid-base pair, weak species. Definitely, yes, a buffer near pH 3, right? What about NH4Cl and NH3? Do your recognition steps. Weak base, yep. Oh, salt. This breaks into NH4 plus and Cl minus. What do we know about Cl minus? We know that Cl minus is the conjugate of a strong species. What do I have here? I have NH4 plus and NH3. Do I have a conjugate acid-base pair? Yes. NH4 plus is the acid and NH3 is the base. If I put about equal amounts of these in a solution, it will resist changes in pH because all you need is a weak conjugate pair. What's the conjugate acid of NH3? NH4 plus. Is that in solution? Yes. Are they both weak? Yes. That's all you need. All right. Now, if I want to ask the question like I asked here, well, if I use this as a buffer, what's the pH of that buffer? If I look up, right, information about NH4 plus and NH3, what I'm most likely to find is that NH3 has a Kb that's equal to 1.85 times 10 to the minus 5. Well, hold on a second. What do I have in solution? NH4 plus and NH3, that conjugate pair making a buffer. What do I need to figure out about what the pH is? The pH is going to be centered around the pKa. But all I know is a Kb. We can't forget, right, those properties of salts, those properties of conjugates that we went over before, all right? We know that if I have a Kb for a base, can I get the Ka for the acid? And the answer is yes. So just remember the version of the Henderson-Hasselbalch equation that we're using always is comparing pH to pKa. There's a plus log term here, but remember we're just kind of trying to identify where that buffer is going to be like set about, where about it's going to be in terms of its pH. So what I'll need to know is what's the Ka of NH4 plus. Always look at your acid. I've identified NH4 plus as the acid. Always look at the acid and figure out its Ka, and then you can get the pKa from there. So this Ka is going to be Kw divided by this Kb. When I do this math, what I get at Ka, and I think we did this before, like 5.4054 times 10 to the minus 10. If I want to know about when I make this buffer, which is definitely a buffer because I see a conjugate acid-base pair. When I make this buffer, if I want to see whereabouts it's centered, right, I'm going to take the negative log of this 5.4054, right, times 10 to the minus 10. And so this buffer would be centered about a pH that's 9.267. So somewhere around pH 9 would be a good sort of tacking point for this buffer. This buffer would be good if I was trying to get a system that was going to resist changes in pH near a pH of 9. Okay? So the only reason I include this example is just remember, you can still do all that work that we know, taking a Kb to a Ka. It still ends up being fed as a pKa into your Henderson-Hasselbalch equation. And just remember, where's the rest of the Henderson-Hasselbalch equation? When we're trying to decide whereabouts a pH is going to be centered, right? We always try to compare, like the last video, one of the last things we said, we always try to compare the pH to the pKa. Okay. You need a conjugate acid-base pair. So, let's do the first part of a longer example, but let's just continue with this line of thought in terms of what we look for. Right? And let's say that we have a system and we want to make a buffer with a pH equal to 4.3. Right? That's what we want. That's our target. And what we're given are two different acids, right, as choices for the acid part of our buffer. And what we're given is, oh, you could use chloroacetic acid, right, which is HC2Cl3O2, right? That could possibly be an acid that we could use in this buffer. Or we could use benzoic acid, which is I think C7H6O2, right? I think that's benzoic acid. Okay. These are two acids we could possibly use. The chloroacetic acid, right, has a Ka that's equal to 1.35 times 10 to the minus 3. Right? The benzoic acid has a Ka that's equal to 6.4 times 10 to the minus 5. So I need a conjugate acid-base pair to analyze this solution correctly, right? But I have a target. So I have a choice to make. I could either use the chloroacetic acid or I could use the benzoic acid. So what do we decide in terms of our choice? What we look for are pKa's. So you're going to get the pKa of each, and whichever one is closer tells you the acid part of your buffer, and then you know the base part because you just make the conjugate. So for example, right, let's do chloroacetic acid first. There's a Ka. I can get a pKa for that situation. And what I get when I do the math is 2.870 as my pKa. Ooh, it's not within plus or minus 1 of that, which again is just a rule of thumb. But it still might be better than this. We just really have to go ahead and figure out what the Ka is, because whichever one is closer, if we only have these two choices, even outside that plus or minus 1, it's whatever one is closer, right? So then I look at benzoic acid, and for benzoic acid, I look at the pKa, and the pKa for benzoic acid, right, is 4.19, right? So now we can see what the choice is, right? The better choice for this situation is going to be the choice where you're within that plus or minus 1. It's going to be the choice where you're closest, all right? Benzoic acid is definitely the choice that you want to use to make your buffer, because it's going to be a better scenario to keep the acid and base concentrations near each other, okay? And it's going to be a situation where you're closest to that pH. pH being close to pKa is what you need for sure. Okay. So then from here we know what our conjugate species should be. If I know that I should use HC7, man, maybe this is H5. Let's change this to H5, and I'll make sure next video what it is in terms of the chemical formula. It ends up not mattering for our analysis, but still just for completeness sake, let's make that an H5. HC7H5O2. If I've identified that as benzoic acid and having the closer pKa to that target, then that's my acid. What do I need to make a buffer though? What I need to make a buffer is its conjugate base in solution with it as well. All right. So what's the conjugate base of this species? Again, we've been doing that for a couple weeks now. What do? You remove the H. So what I want to do is I want to prepare a solution that has this in it and also C7H5O2 minus. Right. That's my conjugate acid-base pair where the acid has a pKa closest to this pH. Now you may kind of get this, I'm repeating things a lot, but it's so important. It's the first step in a lot of problems to identify the correct acid, to make sure you understand that then, okay, this is going to resist changes in pH. It's a weak conjugate acid-base pair. That two-way street would be enacted here. This is the correct choice to start this problem. The next video, we're actually going to get into, okay, now that we know how to choose, right, pKa's for acid systems near the pH, how do we actually enact calculations with the Henderson-Hasselbalch equation, and can we do a couple examples together? And that's where we'll pick up with next time.